So we will continue our video lessons. So we were talking about determinants. So in the previous video, we actually did or learn some properties of determinants, and also we actually saw some theorems. So here we have another small theorem, theorem 4.9. It says that if A is invertible, then determinant of A inverse equals 1 over determinant of A. Okay. So the proof is simple. Here, since it says invertible, that means that matrix A has inverse. That means that here we have A times A inverse, that's equal to I. Now, if you just compute the determinant of both sides, here we have determinant of A inverse, that's equal to determinant of I. So, and also using that, actually in the previous video, we saw that determinant of A times B equals determinant of A times determinant of B. So using that rule, here we can write it as determinant of A times determinant of A inverse. And we know the determinant of identity matrix is equal to 1. So now from here, if you just take this to the right-hand side, since it's invertible, we know that determinant of is not equal to 0. So I can divide both sides by this non-zero number. So determinant of A inverse then is equal to 1 over determinant of A. Okay, that's the proof of this theorem. So let's just see this example, example 9 solution. Given that matrix A has these entries for 4, 3, 7, find the determinants of A and A inverse. So determinant of A in the first part is just 2 by 2 matrix, that's equal to 4 times 7 minus 4 times 3, which is equal to 28 minus 12, that's equal to 16. So now to find the determinant of A inverse, we don't have to find its inverse and after that find the determinant, right? Since using this theorem, then determinant of A inverse should be equal to 1 over 16. All right, here we have another important theorem here. If any matrix A, determinant of A is equal to determinant of A transpose. Right? Of course, when we actually talk about determinant, we know that actually A is a square matrix. That means that this A is n by n matrix. Okay. So here, actually, we consider two cases. Number one is, the first case is, let's say determinant of A is equal to 0. And our second case would be, it's not equal to 0. Let me draw a line here. Okay. So if determinant of A is equal to 0, actually we know that means that this A is not convertible, right? This implies that also A transpose is not invertible, since we have seen that a matrix is invertible if and only if its transpose is also invertible. That means that also determinant of A transpose should be equal to 0. Since determinant of A is equal to 0, determinant of A transpose is equal to 0, that actually implies that then determinant of A is equal to determinant of A transpose. Okay. And how about the second case? Second case is, now we suppose that determinant of A is not equal to 0. So then A is invertible and can therefore be written as a product of K elementary matrices, right? Since it is not invertible, and also we know that if it is not invertible, I mean, if determinant is not equal to 0, that means that A is invertible. And also we know that its reduced to echelon form is equal to I. By applying K elementary row operations, we can reduce A to its reduced to echelon form. And assume that actually those elementary row operations are this A1, E2, E3, dot, 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 and here we have ER. Okay. So now here we are claiming that okay. before we continue here, let me just write something here because we are going to use this fact. Actually, determinant of E transpose elementary matrix is transpose is equal to determinant of E. Right? I'm going to use this fact here. Why is this so? Actually, we know that we have three different elementary matrices. The first one, we can obtain this by interchanging two rows of an identity matrix. And the second one is multiplying a row by K. And the third one is multiplying a row by K and adding this to another row. With the second and third type, we have no problem because we know that actually if identity matrix, let's say here we have this 1, 0, 0, 0, 1, 0, 0, 0, 1. If you just multiply any row by K and transpose this, it does not change, right? Because transposing means it's just, how to say, change your rows into columns. So if you just multiply, let's say this is a second type, okay, if you multiply any row, let's say the third row, 1, 0, 0, 0, 1, 0, 0, 0, K. Okay, and here, as you see here, E2 transpose is equal to E2, because if you just transpose this, it does not change, the same thing. That means that its determinant is equal to itself. Determinant of this E transpose equals determinant of E. And how about the third type? And also by using the property of determinant, if you just multiply any row by K, right, and add it to another row, right, and also determinant does not change, is equal to still, I would say, is equal to 1, because determinant of I is equal to 1. And also first case is true, because if you just interchange two rows and after that transpose this and multiply, I mean, compute is determinant, still you'll get the same result, is equal to 1. Anyway, just taking this as a fact, now since this A, we are just assuming that by applying R elementary row operations, I can reduce A to this reduced echelon form, which is equal to I. And now I can just write it as here, we are assuming that this A is equal to E1, E2, dot, 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 ER. Then what is determinant of A transpose? That's equal to determinant of, here we have these things, E1, E2, dot, dot, dot. Here we have ER transpose. And using the property of transpose, here we have determinant of ER transpose, dot, dot, dot. Here we have E2 transpose and E1 transpose. And by just using the property that determinant of A times B equals determinant of A times determinant of B repeatedly, I can just write it as determinant of ER transpose times determinant of ER minus 1 transpose, dot, 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 determinant of E1 transpose, right? Now, from here, we know that determinant of elementary matrix transpose equals determinant of E. And also rearranging this, I can write it as determinant of E1, because they are just multiples of scalars, times determinant of E2, dot, 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 and here we have determinant of ER. Now, just using the fact that determinant of AB equals determinant of A times determinant of B, so I can just write it as determinant of E1 times E2 times dot, 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 ER, and which is equal to determinant of A. And proof is complete. So now we will talk about one important theorem, that is Cramer's rule and the adjoints, because they are related to each other. Now, actually, this Cramer's rule, first let's talk about this, and after that, in our next video, we will talk about the adjoints. So this Cramer's rule states that if A is an invertible n by n matrix, and B is a vector from n-dimensional space, then the unique solution X of the system AX equals B is given by this formula. Xi is equal to determinant of AIB and determinant of A. To prove this one, first we have to introduce some new notation. See here, you may wonder what we mean by determinant of AIB. Okay, so now here B is a vector from n-dimensional space. So by this AIB, okay, here let's say these are the columns of A, dot, dot, dot. And this AIB means I's column of A is replaced by vector B. This one is vector, is replaced by vector B. And this one is I's column. Okay, dot, 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 and here we have AN. All right. So for example, let's say if you're talking about 3 by 3 matrix and columns are A1, A2, A3, and also B is a vector in three-dimensional space. By A1, we mean this matrix, B, A2, A3. Actually, I should write dot because these are partitions. And by A2, B, that means that the second column is replaced by vector B. So here we have A1, here we have B, and here we have A3. And by A3B, we mean A1, A2, and the third column is replaced by B. Okay, so that is what we mean by this notation. Okay, and also to prove this one now, the columns of the identity matrix I. We know that actually they are standard vectors, right? Let's say this I, that is IN. What is it? Here we have something like this, E1, E2, dot, 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 EN. And each E is from n-dimensional space, is a standard unit vector, right? So here we are talking about this equation, AX is equal to B, right? So now if you just consider this A, I, here we have lowercase I, X. What does it mean? Actually, these are vectors. What does it mean? That means that this I matrix, right, identity matrix, its I's column is replaced by X. So here we have something like this, A. So here we have I equals this. So here we have E1 and E2 dot, dot, dot. And here we have I'th column is replaced by vector X. This one is I's column, dot, dot, dot. And here we have EN. So now, if we just bring this matrix inside, what we have here? Here we have A, E1, because it's defined here. A, E2, dot, 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 and here we have A, X, dot, 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 by the last column, A, E, N. And we know that this A times E1, that's the unit vector. When you just multiply by A, we know that it gives us the first column of matrix A. So here we have, let's say, the first column of matrix A is A1. If you multiply this by A, I mean this unit vector by A, it gives us the second column of A, dot, dot, dot. Here, what is AX? And from the equation, AX is equal to B. So here we have vector B, dot, dot, dot. And here we have AN. Now, what we have here, actually, we got exactly this the matrix A. The only difference is I'th column. This one is I's column, right? It's replaced by vector B. So by using this notation, now it's just equal to AIB. We have this thing. Okay, I need some more space. Okay. So now, here, all right, what happened? So AX is equal to B. Now, if we just, again, here we have on the left-hand side, we have A times IX. On the right-hand side, we have this thing. If we just take the determinants of both sides, what do we have here? Here we have determinant of A times I. Here we have IX, right? On the right-hand side, we have AIB. So that here we have A, sorry, here we have determinant of A, I, B. And we know that determinant of A times B equals determinant of A times determinant of B. So using that theorem, I can just write it as determinant of A times determinant of, actually, not like this, I should write this, determinant of A times determinant of IX. On the right-hand side, we have determinant of capital A, I, B. And we know that actually A is invertible. That means that this determinant of A is not equal to 0. So now we can divide both sides by determinant of A. Then I get here determinant of I, this X, is equal to determinant of AIB over determinant of A. Okay. So actually now we will show that this thing is equal to just xi, i's component of x vector, because our x vector is, what is it, from n-dimensional space, it is like this, right? x1, x2, dot, 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 here we have xi and xn. This xi is the i's component of, what is it, vector x. So if I change from 1 to n, when I equals 1, we get the first component, I equals 2, we get the second component, and if I equals n, we get the last component, and this way we can obtain vector x. So now we will show that why actually that thing is equal to I. Here we have, just let me show you in one example. Here, if I is 3 by 3 matrix, then this IX will be something like this. Here we have 1, 0, 0. And let's say the second one is, changed by this. So here we have x1, x2, x3, 0, 0, 1. So now if we calculate this determinant of this thing, I to x is equal to determinant of 1. Here we have x1, 0, 0, x2, 0, 0, 0. Okay. Here we have x3. And here we have 1. And by using property of the determinant, that if you multiply any row or column by a constant and add it to another row or column, the determinant does not change. As you see here, if you multiply the first column by negative x1 and add to the second column, here instead of x1 we'll have 0. If you multiply the third column by minus x sub 3 and add it to the second row, you'll have x3. So that thing is exactly the same as 1, 0, 0, 0, x2, 0, 0, 0, 1, right? Because you just multiply the first column by negative x1 and add to the second column. Here we will have 0. Multiply the third column by minus x3 and add it to the second column. We will have 0 also here. What is it? It's just, what is the diagonal matrix? So its determinant equals the product of the entries in the main diagonal, which is equal to x2. So if it is x1, I mean I1, we will get the same thing here. So that's why this determinant of I of x is equal to xi. So that's why this gives us actually the solution of one actual component of the solution of, solution vector of this equation. And of course, if you notice here, every time we have to calculate these determinants, it's of course, it's not so efficient way if, for example, our linear system is big, like 4 by 4, 5 by 5. But here, we'll just use this result to obtain, how to calculate the inverse of any matrix by using determinants. Anyway, now let's see two examples, and after that I'll finish this video. Use Cramer's rule to solve the following system. So here, what is our A solution? Let me change my color. Let's use white. So matrix A is, here we have matrix A, it is 1, -3, 1, -3, 5, 7, it is 5, 7, and our vector B is 4, 8. Okay, so let me just write the formula here. What is xi? Xi is determinant of AIB over determinant of A. So in the first step, we have to calculate the determinant of A. Determinant of A is equal to 1 times 7, 7, minus -3 times 5, 15, minus 15, that's equal to 22. Okay, so now x1. What is x1? Determinant of AIB, right? That means that the first column should be replaced by B. So here we will have determinant here. First column, it is 4, 8, and the second column is -3, 7, and over determinant of A, we have already computed here, that's equal to 22, which is equal to 4 times 7, 28, minus, because of this minus is plus, 24 over 22, which is equal to 40, 52 over 22 by 2, it is 26 over 11. And the third step, how about x2? Now the second column should be replaced by vector B. The first column of A is 1, 5. Second column is 4, 8. And determinant of A is equal to 22, which is equal to 1 times 8, 8, minus 4 times 5, 20 over 22, which is equal to minus 12 over 22. That's equal to minus 6 over 11. So now if you just substitute there, you will get, I mean, these are the solutions of the system, dot, dot, dot. The solution of the system are 26 over 11 minus 6 over 11. I've been solving the system using the Cramer's rule. Let's say another example. Use Cramer's rule to solve the following system. Okay, the first step, let's just write our matrices. Here we have A, x1 minus 1, 1. So here we have 1 minus 1, 1. And y is 2, 1, 2. Here we have 2, 1, 2. And z, 0, 1, 3. 0, 1, 3. And vector B is 0, 1, 0. Okay. So we may need more space. Let me draw a line here. And the second step, so let's just calculate the determinant of A. That's equal to 1, 2, 0, minus 1, 1, 1, 1, 2, 3. So immediately, let's see here, if you just add, what is it? Multiply the first row by -1 and add to the third row, what do we have here? At the same time, also, I can just add this first row to the second row. Here we have 1, 2, 0. Here we have 0. Here we have 3, 1. And multiply the first row by -1 and add to the third row. Here we have 0 and 0. Here we have 3, right? And see here, it's just upper triangular matrix, which is equal to 9. 1 times 3 times 3, that's equal to 9. Okay, determinant of A is equal to 9. So now I need to calculate these things. Here, let me just do them here. What is it? First, let me just calculate this. A1B. So the first column is replaced by vector B. It is 0, 1, 0. So the rest is the same, 2, 1, 2, 2, 1, 2, 0, 1, 3. Okay, now here we have 2 zeros. Let me just compute this determinant by using the first column. So it is plus minus. So here we have -1 and delete this row and this column. So here we have 2, 0, 2, 3, which is equal to minus 6. And how about A to B? It means the second column is replaced by vector B. So here we have 1, minus 1, 1. Second column is 0, 1, 0. Third column is 0, 1, 3. So here, okay, the first row contains 2 zeros. So here we have 1, and that's equal to 1, 1, 0, 3, which is equal to 3. And how about A3 of B? Now the third column is replaced by vector B. 1, minus 1, 1, 1, minus 1, 1, 2, 1, 2. And the third one is 0, 1, 0. Okay. All right. So using the third column, right, if you just compute this determinant by cofactor expansion along the third column, so it is here we have plus, minus, plus, plus, minus, plus. So here we have negative 1 times, delete this column and this row. Here we have 1, 2, 1, 2, 1, 2, 1, 2, which is equal to, it is 2 minus 2, that's equal to 0. So now using these facts, we can actually obtain the solutions. Here we have x1 equals a1 of b. Actually, it should be determinants. This is determinant over determinant of a. That's equal to minus 6 over 9. That's equal to minus 2 over 3. And how about x2? In a similar way, a2 of b over determinant of a, that's equal to 3 over 9, that's equal to 1 over 3. And the x sub 3 is a3 of b over, here we have determinant of a, that's equal to 0 over 9, that's equal to 0. So now we can just write our final answer then, dot, 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 the solution of the system is, what is it, minus 2 over 3, 1 over 3, and here we have 0. Thank you very much. Bye-bye.